Hey everyone, welcome back to my channel. In today's video, I'll be discussing another handy little theorem called the Stolz-Cesàro theorem. And this theorem is often called the L-Hopital's rule for sequences, or the discrete version of the L-Hopital's rule. And yeah, this theorem is also pretty useful in solving some in finding out the values of some limits of sequences and all. So yeah, hopefully I'll be able to cover those things in this video. So yeah, let's get right into it. So firstly, let's just quickly revise what sequences are. So sequences are functions of from natural numbers to reals. That's pretty much the most basic definition of sequences. And the next thing is the limit of a sequence. And this part is important because we're going to be using this definition of a limit of a sequence in the parts that follow. So first I'll just spell out the definition for you. So uh, a sequence is said to converge to a limit if for every epsilon positive there exists n belonging to the set of natural numbers such that an minus l is less than epsilon for all n greater than or equal to n. And then we say that an converges to l. Okay, so this means that the limit of the sequence is l. So what does this definition say? Basically it says that as like if you plot the value of the sequence on the y-axis, like you plot the ans and the n's over here, so initially they could have any sort of a value, negative, positive, for all the natural numbers. But what this says is that the further you go, they start to become close to some arbitrary value. So here I have made it close to 0, so I'll say that in this case perhaps an tends to 0, but it could be any value. So suppose this is the L which we are talking about. So if the terms they become close to L, and this and just close to is not a very mathematical thing, right? So the closeness is governed by this epsilon. We can make it anything greater than 0, and for all of these epsilon we can make an as close to L as we want, right? So this was a quick recap of what the limit of a sequence is. So now we can come to the actual meaty part of the theorem. So yeah, so firstly so this theorem has two parts. Now I'll read out both of them. So the first theorem says that if an and bn are two sequences and bn increases to infinity, and the limit n tends to infinity of an plus 1 minus an divided by bn plus 1 minus bn, this limit exists and is equal to L, then the limit of an by bn itself is also going to be equal to L. Cool. And in theorem 2 what we have is that if an and bn are two sequences with an going to 0 and bn going to 0, so yeah, this one is kind of like the 0 by 0 case, and this one is like the infinity by infinity case. So and bn is strictly decreasing, and again the same thing here, that an plus 1 minus an divided by bn plus 1 minus bn, the limit of this as n tends to infinity is L, exists and is equal to L, then so is the limit of an by bn, that is also going to be equal to L. So as I said, what this means is that bn is increasing to infinity, and since this limit exists, it's this one is going to be kind of like an infinity by infinity case. And then so what we're going to do in that is, like, we're going to find out this limit, and if this is L, then we conclude that this is going to be L as well. So this is what we do. And similarly here, this is kind of going to be a 0 by 0 case, and what we do is that we go back to this one, we check this. If this exists and it's equal to L, then we say that okay, this one is also L. So how is this related to L-Hopital's rule? So isn't that exactly what we do in that one? So like we say that there's fx by gx, and if we want to find out, suppose, the limit at some point, and this is coming out to be 0 by 0, what we do is we find out f dash x by gx, limit of this. And of course there are a lot of conditions involved for us to be able to do this, but I'm just kind of um, explaining this and skimming over those conditions here. So if this one exists and this is equal to some L, then what we say is that this one is also L, right? If this exists. And here, what is the derivative here? So this thing is kind of like the discrete derivative, isn't it? Because you're finding f of, in here what does f dash x mean? We are doing f of x plus h minus f of x divided by h, limit h tending to 0, right? That is what we were doing for a derivative. So here this h, we really can't go smaller than 1, so this is kind of a n plus 1 minus a n, and again in the denominator we can't go any smaller than 1 since we are dealing with natural numbers. This is kind of like the discrete derivative, sorry, yeah, derivative. Cool. So now we're going to try to prove these theorems. So I'll just prove the second case and you can try out the first case. It's pretty similar to the proof of the second case. So yeah, as I said, I'll prove theorem 2. So how I'm going to do it is that I assume the hypothesis, which is that the limit of an plus 1 minus an divided by bn plus 1 minus bn, this limit n tends to infinity, this is equal to some L. Okay, so what this means is that I will use the epsilon definition which I had mentioned earlier. So what this means is that for every epsilon positive exists some n not belonging to natural numbers, such that now I use this fact that an plus 1 minus an divided by bn plus 1 minus bn minus L, this is less than epsilon for all n greater than equal to n naught. Cool. So yeah, so here we have that, and what we can rearrange this kind of, we'll use the properties of the modulus. We'll write this as an plus 1 minus an divided by bn plus 1 minus bn minus L. This is less than epsilon and greater than minus epsilon. So this rearranges to give us that an plus 1 minus an divided by bn plus 1 minus bn is less than L plus epsilon and less than uh, greater than L minus epsilon, right? So this is what we have finally. So now we're going to try to manipulate this part. So let's move on to the next page. So here what we'll do is that we'll this is L minus epsilon, and now what I'm going to do is that I'll just rewrite this here for now just so that we don't miss a trick, and this is L plus epsilon. Now we are in the hypothesis, if you recall, we are given that Bn is decreasing. So that means that Bn plus 1 is going to be smaller than Bn. So this quantity is a negative quantity and it's strictly decreasing, so it's not 0. So I can kind of multiply this out over here. So what we get is that we get Bn plus 1 minus Bn into L minus epsilon is less than An plus 1 minus An is less than I'm so sorry, this one, since it's minus, the inequality is going to reverse, so this inequality will reverse, so this one is going to come over here, L plus epsilon, and this one on the left one is going to come on the right. It's going to look like this. Okay, so now we have this inequality, and this holds for all n greater than this n naught, right? So now what we're going to do is that we're going to sum this up. So we're going to sum up all these ones, this one, and this one. From where to where? We're going to sum it up from n varies from capital N to some n prime. And we're going to sum up this one from n equal to n prime, where of course n is some number which is greater than n naught. Cool. So when we sum this up, this is a constant, so this is going to come out, and this is going to become a telescoping sum, right? So the alternating terms are going to cancel. What I mean is that this is bn plus 1 minus bn. Next term we're going to add bn plus 2 minus bn plus 1. This one is going to cancel. Similarly, in the next term it's going to cancel. So in the end, what we're going to be left with is that we're going to be left with only two terms, which are, this is L plus epsilon. This comes out. This one becomes b n prime plus 1 minus, and over here we're going to get bn. Over here again similarly we get an prime plus 1 minus an, and over here what we get is L minus epsilon times b n prime plus 1 minus bn. Alright, so now what's the next step gonna be? So what we'll do is that we'll divide we'll divide all these by bn, capital N, right? B sub n. So what we get is that L plus epsilon into bn prime plus 1 by bn minus 1 is less than a n prime plus 1 by bn minus a n by bn, alright, is less than L minus epsilon into bn prime plus 1 divided by bn minus 1. Alright, and now we're gonna use something. We're gonna try to use our initial hypothesis, which said that both an and bn, ans and bns both approach to 0 as n tends to infinity. So just note that here we had chosen n prime to be independent of any of our it's independent of this n, it's independent of epsilon, it's independent of this n naught, right? This only condition is that n prime has to be greater than n naught. That's all. So we are free to make n prime as big as we want. So what happens when n prime tends to infinity? So what happens is that this is a constant, right? But bn prime plus 1, what happens to this? So as n prime tends to infinity, bn prime plus 1, this must tend to 0 by our initial hypothesis that bn and an both tend to 0. So this term is going to go to 0 applying the limit. So I'll just write this here, limit n prime tends to infinity. Under that condition we have this tends to 0. Again bn is a fixed constant for now with respect to this an prime. So again this an prime tends to 0, so this goes to 0, and so does this go to 0. So what we're going to be left with is that we're left with L plus epsilon into minus 1 is less than minus a n naught by not n naught, sorry, an by bn is less than L minus epsilon into again minus 1. Alright, and this again, let's not forget, holds for all of these. This n is just some number which is greater than n naught. Let's not forget that. So again now we are going to cancel out this minus sign, but that's going to reverse the inequality. So I hope you're okay with that. Or you could just say that we take this one here and we consider this separately, and then you consider this inequality separately, and once you rearrange, what you're going to get is that an by bn is less than L plus epsilon. It is greater than L minus epsilon for all n greater than n naught, right? And finally when we rearrange, we get that an by bn minus L, the mod, is less than epsilon for all n greater than n naught. But this is precisely the epsilon definition of the limit, right? So what this proves is that the limit of n tends to infinity, an by bn, it is equal to L, or you can say that an by bn tends to L. Okay, so here we have that. So now let's just quickly have a look at some applications of the Stolz-Cesàro theorem, and I'm sure this will help you to apply this theorem to some problems as well. So yeah, so firstly let's have a look at the problem. So it says that there is a sequence an whose terms tend to L as n tends to infinity, and you want to show that the sequence defined by the average of the first k terms, which is like the am of the first k terms of an, and you want to prove that this sequence sk also converges to L. So if you think about it, it's a pretty natural statement, because the this sk's are going to become increasingly close to ans as we make k larger, because of course the uh, as an tend to L, so it's gonna, the terms are going to become closer and closer to L, and so, and there are infinitely many terms which are close to L, so of course it's going to get biased towards L. But how are we going to prove it? So of course, since this is a video on Stolz-Cesàro theorem, we're going to be using that for this one. So here let us take the numerator of the numerator over here, let's take this part to be some sequence ck, and this one let's call it dk for now. Alright, so what we have is that dk is an increasing sequence, dk which is k, it is an increasing sequence, this is check, and it increases to infinity, this is check. So definitely we're going to be using theorem 1, if you recall that one, right? So this does satisfy the hypothesis of theorem 1. And what that theorem did say is that if we can find that ck plus 1 minus ck divided by dk plus 1 minus dk, if this one exists as k tends to infinity, then if this exists, then we can say something about sk as well. So let's check out what this becomes. So this is going to become the sum of a, it's called ap, p where is from 1 to k plus 1 minus summation from p equal to 1 to k ap, right? And in the denominator all it's going to be is simply k plus 1 minus k, which is simply 1. So this one is going to be, I'll just write k tends to infinity, and so this one is simply going to become limit of k tend to infinity of a k plus 1, and of course this is simply the limit of k tend to infinity of ak, of course adding 1 to infinity, that's not really going to make a difference. So these limits are going to be equal, and this limit is actually going to be equal to L, as we know. So what this gives us is that the limit and k tends to infinity of ck plus 1 minus ck divided by dk plus 1 minus dk, that is equal to L. So what this means is that the limit of k tend to infinity of ck by dk, which is actually the limit of k tend to infinity of sk, that is going to be L, which is exactly what we wanted to prove. So this is hence proved. Alright. Let's have a look at the next illustration. It says that given that this infinite series summation of an from n equal to 1 to infinity converges, we want to prove that the limit n tends to infinity, n into an is equal to 0. Alright, so yeah, so how are we going to start looking at this? Well, there are several ways to do this, but I think the easiest way is to use Stolz-Cesàro theorem. So how are we going to use this? So firstly, just note that since this series converges, it must be converging to some value, right? So we can call it, let's call it equal to m. Okay, this the value of the summation of this series. So what this gives us is that uh, now what we're going to do is we're going to try to apply Stolz-Cesàro theorem in some way. So let's consider a sequence, let's again call it Cn, let it be the sequence given by n into summation of an from from k equal to 1 to n. Okay, and let dn be nothing but this. So again we have that dn is increasing to infinity, so again we're going to be using theorem 1 of this Cesàro-Stolz theorem. So what is going to happen is that we have that cn by dn, this is kind of like an infinity by infinity case. So what we're going to look at is the limit of n tend to infinity of cn plus 1 minus cn divided by dn plus 1 minus dn. Alright, so the denominator is 1 as in the previous case, but the numerator is actually going to look a bit different. So this is going to be k equal to 1 to n plus 1 into ak minus n into summation of ak from k equal to 1 to n. So what is this going to look like? So this is gonna become n plus 1 into an plus 1. Alright, we're gonna keep that separately, and then this is gonna be n plus 1 into summation of k equal to 1 to n plus 1 ak, and minus n into summation of, sorry, not this, k equal to 1 to n ak, right? So clearly this term is going to cancel the coefficient of n, and we're going to be left with simply, let me erase the screen. We're going to be left with n plus 1 into an plus 1 plus the summation of ak from k equal to 1 to n, and this is the limit of that ck plus 1 minus ck divided by dk plus 1 minus dk. So this is what the this is gonna look like. But just remember that we know that limit n tends to infinity ck by dk, what this is, because we know we had taken ck to be this ck to be n into summation of n, and this one to be nothing but n. So if we just can get rid of this n, so what this is that this is n summation an divided by n. You can get rid of this n, and this summation from k equal to 1 to n, this is actually gonna tend to, as n tend to infinity, this is convergent, so we know that this is tending to m by our hypothesis. This is nothing but m, so we have that this is equal to, this limit is equal to m by Cesàro-Stolz theorem, because since this is equal to m, therefore the discrete derivative, if we take that of the numerator and the denominator, that limit must also be m. Okay, so now also note this, what is this? This is also m. So what we have is that we have n plus 1 into an plus 1 is plus m is equal to m, and we get rid of this m, we get that n plus 1 into an plus 1 is equal to 0, as of course limit n tends to infinity. I kind of forgot to write that over here, but anyway, so yeah, so of course as n tends to infinity, it really doesn't matter that whether there is an n here or there is an n plus 1 here. But if you really want to write that for sure, then we write this as n into an plus 1 plus an plus 1 is this is equal to 0. Now one last trick which we need to use is that um, that when a series converges, then the terms of the series themselves go to 0. Okay, why does this happen? Because of course if they do not go to 0 as n tends to infinity, then you're going to be adding some finite value, let it be alpha, suppose they tend to alpha, then you're going to be continuously adding alpha as n tends to infinity, and you're going to be adding it infinite times. So whatever the sum is, you're going to be continuously adding some values to it which are not getting any smaller. So yeah, that makes it impossible for the series to converge. So that's what happens. So that's why in this case, as n tends to infinity, this term goes to 0, and the limit of, as we know that n tends to infinity of an plus 1, that is equal to the limit of an. So thus we get that the limit n tends to infinity n an, this is equal to 0, as we wanted. Alright. So yeah, that's all the stuff I have about Stolz-Cesàro for you for now. But yeah, quick shout out to Harishankar sir. He introduced me first to this concept, and he writes a lot of nice answers on Math Stack Exchange. So I recommend you to go and check that out. I'll put the link in the description below. And yeah, as always, please be sure to like, subscribe, and if you have any suggestions, or if you would like me to make videos on some other particular topics, then please feel free to comment them down below. And yeah, see you next time. Bye.